Alright, so in our last video, we were introduced to this concept of moment of inertia, also known as the second moment area. And this is really our means to sort of define what the distribution of our area is away from the centroid. And it's really a means of, trying to determine, what our resistance is to rotating a given, cross-section around a given axis. And we really started with the centroid of that axis, and we started with this sort of rectangle, and we derived that the moment of inertia about the centroidal axis is 1/12 times the width times the depth, and the depth just being, the perpendicular distance from the axis you're rotating about. So 1/12 times the width times the depth to the third. And that was, pretty straightforward. And, we didn't derive these, but if we look at some other sort of similar sections which we're rotating about their own centroidal axis, we find that with a triangle rotated about the centroidal axis, that its moment of inertia is going to be 1/36, so just 1/3 of what it is for a rectangle, 1/36 BD cubed. And then for a circle, our moment of inertia is 1/4 times pi times the radius to the fourth. So we didn't derive these two, but you can just sort of take these, my word for it, and if you did want to work through the derivations, again, it's very similar to how we did with the rectangle. And that's all well and good, and the rectangular section is quite useful for us because in structural engineering, a lot of our elements that we work with are rectangles. So lots of beams are made out of rectangles. So if you think conventional timber framing, you're looking at 45 by 90 millimeter timber joists, or 45 by 140. They're rectangles. We don't get a lot of triangles, but we'll have things where we'll have holes in them. And this was useful, but not every element is made of a rectangle, and there sometimes we will get these sort of compound sections. And this is also what we looked at is, if we have a compound section, we can work out, what the moment of inertia is as long as each of these pieces shares the same centroid. And so, again, just as a quick recap, if we're going to try to find the moment of inertia of this compound section, which has this rectangle hole taken out of it, well, the moment of inertia would be the, Ix equals the moment of inertia of the outside minus the moment of inertia of the inside void. And so if we drew this as a picture, that would effectively be some total width out here that has some width b and some depth d, and we're going to subtract out the middle here, where if that is our exterior, we're going to subtract out this middle that has some width b1 and some depth d1. And so if we wanted to write this out as an equation, Ix equals 1/12 times b times d cubed minus 1/12 times b1 d1 cubed. So again, this is all pretty straightforward. It's just effectively we've got two rectangles, and as long as we're sharing these two rectangles share the same centroid, we can just simply take the sum of their moments of inertia. In this case, the moment of inertia of void, we're going to subtract it out. And so that's it with a rectangle. Well, what if we have a circular hole? Well, again, it's much the same. It's going to be Ix equals the moment of inertia of the outside. So this whole rectangle here minus the moment of inertia of the void. And again, if we're to draw this pictorially, we would have some rectangle minus some circle. And the circle has, radius r. The square has a width b. A rectangle has a width b and a depth d. And so just like we did with the rectangular void, it's much the same. Because these two share the same centroid, we can just simply subtract them out. Equals 1 over 12 times the base times the depth cubed minus 1 over 4 times pi r cubed. Sorry, pi r to the fourth, not pi r cubed. So that's that, and this should feel, pretty straightforward and analogous to how we calculate centroids, where, we could be just adding or subtracting areas as needed. And I keep making this point of we can do this if all of our shapes, share the same centroid. But, not every shape does that. Not every cross-section has all of its little constituent components with the same cross-section. And again, you can think about, say, this rectangle. It depends upon how you wanted to break it up. We broke it up with, two rectangles which had the same centroid. But if we thought of it like in terms of flanges and webs, well, the flange doesn't have the same centroid as the web, so, that might lead to a little bit of a thought of like, well, there might be something different going on, and we might need another tool. So to look at that, we're going to look at an eye section, and we're going to try to analyze it using the same method, but sort of in two different ways, and then we can see why it's so important that we can only just do the straight subtraction, or adding and subtracting, of moment of inertias of the constituent pieces if they have the same centroid. And so our example for that will be just this eye section, which both the flanges and the web are of 10 millimeter thickness. It's 100 millimeters wide and 200 millimeters deep. So we're going to try to calculate the moment of inertia in two different ways. All right, so our option number one is we will do, much the same as we did here, where we'll just sort of pick some components which are effectively going to share the same centroid. So, if we have our eye section here, and we know that our centroid is across here, well, we can think around, we'll draw our voids in red. Well, effectively, we've got, our voids have their centroid sitting right here, and we've got some, exterior of the whole section has its centroid sitting right there. So this would be equivalent to, some outside bit of distance 100 and a height of 200, and it's going to subtract out effectively two of these voids. So if we sort of draw our cross section here, so it'll subtract out a void from the left-hand side and a void from the right-hand side. and both of those are going to be 45 millimeters wide and 180 tall. So that's quite simply, if we were then to work this out, we'd have I xx equals 1 over 12 times 100 times 200 to the third minus 2 times, because we got 2 of these, 1 over 12 times 45 times 180 to the third. And if we work all of that out, we get Ixx equals 2.29 times 10 to the 7th millimeters to the 4th. So that should feel like nothing, strikingly new from what we've already done. It's effectively doing the same thing as we did with these voids, which are sitting in the center. And then this only works because the centroid of each of these little pieces is all along this xx axis by which we're taking our moment of inertia about. Now, let's take option 2, and we're going to do it. I'm just going to tell you from the get-go that what we're going to do is not going to work out, but I kind of want to show you why. So, option 2, just sum of flanges and web, and just to state it, this won't work out. But I do think that, it's important to have this illustrative example because it'll show you why it's not going to work out, and that we do need to have, we're missing one piece if we simply just sum up the moment of inertia of each of these little pieces. So this would effectively be, we'd have the top flange, the web, and the bottom flange. This is 100, 10, 100 wide, 10 thick, 180 wide, 10 thick. So I of the flange is simply going to equal 1 over 12 times 100 times 10 to the third, and that equals 8,333 millimeters to the fourth. I of the web equals 1 over 12 times 10 times 180 to the third, and that equals 4.86 times 10 to the sixth millimeters to the fourth. And I of the flange down at the bottom, it's just going to be the same as the flange at the top. 1 over 12 times 100 times 10 to the third. That equals 8,333 millimeters to the fourth. So then if we go I total equals I web plus 2 times I flange, that equals 4.86 times 10 to the sixth plus 2 times 8,333. We get I total equals 4.87 times 10 to the 6th millimeters to the 4th. So now this should start raising alarm bells. We've got 2.29 times 10 to the 7th and 4.87 times 10 to the 6th. We've got very different numbers here. In fact, let's just work out what our difference is. We've got 4.86 to the 6th divided by 2.29 to the 7th. You know, this is only 20% of the actual moment of inertia. And this should mean that we're missing something, missing some component. And effectively, the component that we're missing, and the reason that we get different answers if we just simply sum up the moments of inertia of each of these little pieces versus if we take the moment of inertia of these whole things, is really has to do with what axis we're rotating these little bits and pieces about. So if we're moving something around the centroid, its own centroid, it's actually, relatively easy to spin. A phone's just going to spin like that. But if we rotate it about a different axis, it's a bit harder to spin, And you can do this with, I just grabbed a phone here because most folks have a phone in their pocket. And you think if you spin right at the center of the phone, it's kind of easy. And if you hold at the end of the phone, it's a lot harder. And it's that additional bit of sort of rotation, if you think about it as another moment, really what we're missing is, for these flanges, what is the additional effort it takes to rotate this whole area, not just about its own centroid, but about some distance to the major centroid. And that's what accounts for this other 80% of our, moment of inertia. And the component that we're missing is that. And so the way that we deal with this is we use what's called the parallel axis theorem. So and we'll just write this out. So when not rotating a shape about its own centroid, we need to use the parallel axis theorem. And this is the parallel axis theorem in a lot of ways is one of the most powerful tools in all of structural mechanics. And I'll write it out here, and then we can sort of talk through each of the little bits and pieces. So if we have the total moment of inertia is simply going to be the sum of I equals 1 to n, so this is just all of the little pieces of I, x, x, I. Now this, if we stop right here, this is effectively what we've done so far, when we did these examples. We just simply summed up the moments of inertia of all the pieces. But as we saw in our little, I section example, if we just do that, we're missing potentially up to 80% of what the moment of inertia is. And so what's this other bit? Well, it is the area of each little piece multiplied by the square distance to the centroid. So this is the parallel axis theorem. And so let me just write out what each of these pieces means. So IXXI is the moment of inertia of a piece of cross-section. AI is the area of a little piece of cross-section. And DI is the distance of a little piece it's the distance from the centroid of a little piece of cross-section to the centroid of the whole cross-section. Or some axis of interest. All right, now we won't go through a formal derivation of this, but one way that I like to think of it is that, when we worked out what the moment of inertia was in this, second moment area, it's just a y squared dA, second moment area. That's also a moment of inertia. Recall that it's going to be, y squared dA. And that's really for, if we're trying to look at some engineering blob, it has some centroid here. We've got a little piece dA, and we want to know, its y distance. But this is really for if we're bending about, this some axis here about the centroid. And recall that all this is doing is you're thinking about, well, what's the effort? So if you think of dA as analogous to a force, well, it's sort of the moment multiplied by the distance again. So this is y squared, second moment area. So you can think of it like the moment of the moment about this bit. And that's really just, how hard it is to spin about the centroid. But if we want to go around some axis that's not the centroid, so this is G, and we want to say we want to come around some axis down here. Well, this will be some D. We still have this little dA. It still has its own little distance y. But this whole bit has some total area A. And so this is where you can think of, I xx of I plus ai d squared of I. You can think of this as like, micro moment of inertia. This would be like macro. Moment of inertia. Where really, upon inspection, we're doing much the same thing, where if, I equals, we take in some little area, multiplying by its distance to the axis we're spinning around squared, well, we effectively want to know that this thing itself can spin about its axis, and then it can also spin, it's got some additional effort to spin it around an axis which isn't its centroid. So it spins pretty easy here, and it's a lot harder to spin, about the bottom. And again, this is much the same, where we're just taking some d squared, so some total area, which here, dA integrated over a equals a, times some distance squared. So you can think we're just really doing this, again, we're just accounting for not only what the effort is to spin this little piece about the centroid, but this each and every little piece about the centroid, and this whole area about some given axis. Now, you can also see that if we were spinning around the centroid, the distance d to the centroid goes to 0, and then we just end up with this here. So I think we'll sort of skip on to an example and sort of show how this would work for a rectangle about an axis which is different than its main axis, and then we'll go back and we'll have a look at sort of a couple of examples we'll sort of revisit this example here. So say we wanted to find I of, AA, where the centroidal axis is our x-axis, and the top of this rectangle is the AA axis. We've got some depth, we have some depth, and then obviously d over 2. So this is just to prove that, we could go about any axis, and we could easily take this and then use it on a compound section where this might be a flange. But we'll just show it with just a simple rectangle to start with. So our total moment of inertia is the sum of I xx plus a sub I d sub I squared. We only have one element, so I equals 1. So that's simply going to be the moment of inertia of the rectangle of its own little piece, which is going to be bd cubed over 12, plus the area, which is b times d, times the distance of the centroid of the little piece to the axis that we want to go around, which is simply going to be d over 2 squared. So I total is bd cubed over 12 plus bd cubed over 4 if we expand this out. And then we can, do a little bit of algebra, factor out the bd cubed, we get bd cubed equals 1 over 12 plus 3 over 12. And so I total for A, so about this top axis, is simply going to be bd cubed over 3. All right, so that's sort of that bit there. Now, So that's just how to apply the parallel axis theorem, on a simple rectangle. Let's go back to our option 2 example. So to revisit, the I section. Now, we know that we've got some little centroid of each piece. 100, 10, 180, and 10. So we can work out if we've got, we know that I total is simply going to be the sum of each little piece plus the area of each little piece times its distance to the centroid squared. We know the centroid is 100 millimeters. So let's start with, we'll just sort of write all of this out. We know that we'll come down here where we need a little bit more room. I total is simply going to be I flange plus area of flange times d flange squared. So this is the distance from flange centroid to section centroid. And then we're going to do the same thing for the web. So I web plus A web d web squared and plus I flange plus A flange d flange squared. So because these are symmetric, we can just multiply this by 2, but let's work out these pieces. So we'd have I flange equals 1 over 12 times 100 times 10 to the third. And we already worked out that that's simply going to be 8,333. Millimeters to the fourth. I web, again, is 1 over 12 times 10 times 180 to the third. And we've worked out previously, that's 4.86 times 10 to the sixth. Now we need to work out the area of the flange. Is simply going to be 100 times 10,000 millimeters squared. The area of the web is 180 times 10, which is going to be 1,800 millimeters squared. The distance between the flange centroid to our x-axis is simply going, well, we know that this is located at 5 millimeters up from the bottom because it's just halfway. So it's going to be, 200 divided by 2 minus 5. So 100, this is simply going to be 95. That's 200. And we know that this distance is 5. And so df equals 5 millimeters, and d web equals 0 millimeters because the centroid of the web is located at the centroid of the total section. So if we plug all of this in, and knowing that we can just multiply out these two flanges, we would get I total equals I web plus a web d web squared plus 2 times I flange plus the area of the flange times d flange squared. So this is simply going to be 4.86 times 10 to the 6th plus 1800 times 0 squared, so that goes to 0, plus 2 times 8,333 plus 1,000 times, now here's where we're going to end up with the sort of our discrepancy, because until here, this is effectively what we had previously, was, I flange plus, so I of the web plus 2I flange, I of the web plus 2I flange, and then this is this last bit, is this 1,000 times our distance to our flange is not 5 millimeters, sorry, it's 95 millimeters. Again, 95 from the centroid here to here, times 95 squared. So what we can do is we know that this is going to end up equaling, let's just run our math real quick, it's 4.86. So we get 4.86 to the 6 plus 2 times 8,333 plus 1,000 times 95 to the 2. And we get just the same as we did previously. I total equals 2.29 times 10 to the 7th. So it was this portion here, this AD squared, which is the missing 80% of what we needed. And really it was all about, what the effort is to move these flanges around the centroid. So do basically this revisit I section, but calculate properly. So that's in essence, that's our example of the parallel axis theorem. Like I said, it's a really powerful tool, and you'll find that, you can actually, if you just apply the parallel axis theorem, it will work whether you're going about the centroid or any other axis, because if you're going about the centroid, this d becomes 0. If you're going about any other axis, this d is just whatever the distance of the piece you're moving, the centroid of that piece, to whatever the axis is that you care about. So just like this here, from the centroid to whatever axis you care about. Say we call this A. So I hope you found that helpful. In the coming videos, we'll just run through a number of examples of this, and so hopefully it will become second nature for you. So with that, thanks for watching.